now that we have the work energy theorem, let us see how we can apply it. We're going to start with something simple, something whose answer we already know. And the purpose of that is to see whether our new method applied to the same problem will give us the same answer as it should. And also you can compare the method, this new method, against the one we already know. And to this end, we're going to start with a very simple problem, the freeform. Okay, now suppose we have a particle moving either up or down with initial speed vi, and it's powered by gravity only. My question is, after going down by distance h, if the initial speed is vi, what is the final speed vf equal to? Again, this is something we know how to do from chapter 2. And so we have a uniformly accelerated motion, one-dimensional motion. Everything happens on a vertical line. And we have v initial, we're looking for v final. We know the acceleration, which is g. We know the displacement, which is h, along the same direction as g. So without knowing the time it takes to go from initial to final spot, the simplest way to do that is to use the well-known formula for uniformly accelerated motion, and that is v final squared minus v initial squared equals to 2a delta x. That's the generic formula. Now, in our case, we're looking for v final, given v initial, so v final squared minus v initial squared. What is that equal to in our case? A is g going downwards. Let's choose downward as positive, so a is positive g. And delta x is the downward displacement, which is h. So you can easily find v final. V final equals to the square root of v initial squared plus 2gh. That's the quickest way we learn how to do from chapter 2, uniformly accelerated one-dimensional motion. Okay, now, can we get the same result with the work energy theorem? It could be an overkill, but at least we can see whether it reproduces the same result or not. All right, so in this case, as with any problem involving the work energy theorem, you must decide two states, one initial, one final. But right now, we already know what that is. V initial is where it starts. V final is after it drops a distance h below the original height. And we can link these two states by applying the work energy theorem. W equals delta k. Okay, so we have W equals delta k. W initial to final. Now, in this case, the only force that powers the motion is gravity, and we only have to consider work done by gravity. We have already learned how to do that. That's mgh. H is the distance dropped, so the gravity does positive work in this case, mgh. Okay. And that equals 1/2 mv final squared minus 1/2 mv initial squared. That's delta k. 1/2 mv final squared. Then minus 1/2 mv initial squared. Okay, what are we looking for? Looking for v final. You see, the mass is crossed out, so it turns out the mass doesn't matter. We can cross that out. As expected, anything that's powered by gravity, the mass does not affect motion, because when you double the mass, you also double the force of gravity. Therefore, the acceleration, velocity, displacement, they all stay the same. Okay, so we're just looking for v final. Now move that 1/2 v initial to the other side, and then move that 2 over. You just and then take a square root. You get the same result. Okay, so v final equals the square root of v initial squared plus 2gh. That's exactly the same result as before, as it should. Okay, now, do we see a distinct advantage of using the work energy theorem compared with the old method? Not really, not in this case, because the old method is already simple enough, but at least gives us a new way, a new approach. Okay, we have another choice when it comes to solving problems like this time. Now, let's look at the second problem. This one, you can start to see the advantage of applying the work energy theorem. And that is, we're going to start to move away from vertical lines, so we don't just have a free fall, we have a projectile motion. This problem you have already seen before as well, and here's the problem. We start we project a projectile starting from the origin of a coordinate system, okay, and it's got a certain initial velocity, v naught, making an angle phi with the horizontal x-axis. Question is, after the thing goes up by distance h, okay, assuming it goes up first, what is the speed of the projectile, object, after it goes up by vertical distance h? Well, this problem belongs to chapter 4, and we know how to do that from chapter 4. The idea was to break down the motion into x and y direction, and then that tells us what Vx is and what Vy is. Then you can just add them together by combining the horizontal and vertical components. So, you know, that's the strategy, right? We break down the velocity into x and y direction, Vx and Vy, and then you find Vx and Vy, and then you combine them, okay, by using the Pythagorean theorem. So let's do that. Let's see how we can do that first using, you know, the old method from chapter 4, and then we can see how we can do this with our new method. Okay, so what's Vx equal to? Vx is the x component of the final velocity. Now Vx doesn't change; it's the same as Vx initial. So let's write that down now. Okay, so Vx equals the initial value, which is v naught cosine phi. That's it. Do we know what the angle phi is? Yeah, but it turns out at the end that angle phi doesn't even matter. Okay, but right now it is in the expression of Vx, so we're going to keep it. What about Vy? Now that is different from Vy initial because there is an acceleration. The formula to use is V initial plus AT because it's uniformly accelerated motion. V initial here is in the y direction, and the answer is V naught sine phi. That's initial value, V naught sine phi. And then plus ATA is negative G. If you choose the upward direction, it's positive. That's the convention. So minus GT. Now the problem here is you have to know what T is, right? And of course you can solve for T, you know, using the information about Y or H in this case. Y equals H, right, for the final position. So you can use Y equals, you know, Vy initial T, then minus 1/2 GT squared. You can find H. You can find T, which you plug into this expression for Vy. Then you can get Vy. But it's a mess. Okay, there's a lot of calculation, and we're not interested in T, the time it takes to get there. We just want to know the final speed. Can we bypass the knowledge of T? Can we find Vy final directly without using T? Yeah, we can do that. There is a formula for uniformly accelerated motion without T in it. It's the same formula we saw earlier, this one right here. Okay, this first one right here. Okay, we just replace X with Y, that's it. All right, so let's go back. Instead of this, of course, this is valid, but we're not going to use it. Okay, so I'm going to cross this one out. In fact, I'm going to write this and I'm going to cross it. I'm going to cross it out with a different color. It's not wrong, but we have a better way to do this. So we have Vy squared minus Vy initial squared, V initial Y squared equals to 2ay delta y. Okay, that's the generic formula in the y direction. And Vy is what we're looking for. So Vy squared minus, what's the initial value? That is V naught sine phi, right? Squared equals to 2ay, which is 2 times negative g. Okay, ay equals negative g because the upward direction is positive. So the acceleration is downward, therefore it's negative. Delta y is just h from initial to the final, the vertical ascent. The vertical change in displacement is h, so that's h right here. And that tells me what Vy is. So Vy, in fact, let's just find Vy squared, because that's what it takes to find V eventually. We just move that V naught cosine theta to the other side, or sine phi to the other side, minus 2gh. Okay, so now you have Vx and you have Vy. let's combine them. Okay, so now we have V equals to the square root. Let's redraw this. Sorry, I just want to draw a better straight line, that's all. Okay, that's better. Vx squared plus Vy squared. Right? Let's do that. Let's plug the value of Vx and Vy, the expressions of Vx, Vy. Okay. And then Vx, as you know, is Vo cosine phi, and you square that. And then Vy squared, we already have that. That's Vo sine phi squared minus 2gh. All right. Now, interestingly enough, you look at the first two terms inside the square root sign, is V naught squared cosine phi squared plus V naught squared sine phi squared. If you take that V naught out, okay, if you take that V naught out, you're going to get V naught squared. And what's left is what? Cosine phi squared plus sine phi squared. And then minus 2gh. Now we already know, everybody knows what this is. This equals 1. So curiously enough, the angle phi makes no difference for the to the final speed v. Okay, and the answer is the square root of v naught squared minus 2gh. All right, it's just a minus sign instead of a plus sign that you saw in the solution to the first problem. And the reason why there's a negative sign is because it's going up. So gravity is against it, so you're going to end with smaller speed. That's why it's a minus sign. And the angle phi disappears. Okay, the angle phi disappears. Now, this is not a hard problem, but we still had to break it down xy direction. And it turns out the initial angle of launch phi makes no difference. But what is the physics in it? How come the angle phi doesn't matter? Is there a simpler way to find the final speed? The answer is yes. And the answer lies in the work energy theorem. Okay, so let's add a page here. I want to revisit this problem using the work energy theorem. So the work energy theorem. For the work energy theorem, I must choose initial and final state. So going back to here, I have these two states. Here is my initial state. Okay, that's I. And then here's my final state. Oh, that's final. Okay, I'm going to relate these two states using work energy theorem. So let's do that. From the work energy theorem, I have W initial to final equals delta K. Okay, who is doing work? Gravity. Okay, gravity is the only force. And how much work does it do? Well, the thing went up by distance h, vertical distance h. Gravity does negative work. How much negative work? That would be negative mgh, right? And delta K is K final minus K initial. K final is 1/2 m v squared. Okay, we didn't use v final, we just call it v. Minus K initial, and that is 1/2 m v naught squared. The angle phi has no position in the expression for delta K. So it doesn't matter. What are we looking for? Looking for V, okay? So solve for V. Cross out the mass. Again, the mass doesn't matter as it shouldn't. Mass, and mass. And we just move the two, multiply everything by 2, and then, move this 1/2, move this mv naught squared term to the other side. And so we can essentially solve for V, and we get V equal to square root of V naught squared minus 2GH. Wow, look at this. It's the same answer as that. Same answer as that, except it's a whole lot faster, right? And you can see clearly that the angle phi makes no difference, just like the direction of the final velocity. This angle it makes with horizontal, it makes no difference either. Okay, the physics here can be easily explained, and that is in going from initial to final position, the only force that did work was gravity, and that work changed to kinetic energy. Okay, and since work and energy, these are all scalars, the direction of motion, initial, V final, will have no effect on the outcome of the final speed. So this second problem, you can already see, even though we got the same answer as before, this is a more efficient solution. Okay, so this is certainly a case where the work energy theorem start to take advantage of the situation, giving you an easier time solving the problem. But before we end this lecture, let's take a look at the first problem we posed at the beginning of chapter 7. This is a problem that we couldn't do with F equals ma in its original form. Recall that problem? This problem here, right? You have a block sliding down frictionlessly along a smooth track with no friction, but the detailed shape of the track is unknown. After dropping a vertical distance h, how fast is the final speed? When you're given initial speed, you're given the fact that it's a smooth track with no friction, and you're also given the vertical drop, but you do not know the details of the shape of the track. How do you find the final speed? Again, don't start with F equals ma in its original form, because it's not going to give you an easy answer. But we can try to work energy theorem relating initial state and final state. Okay, we have initial state right here. The initial state is right here. And with the final state at the end, of course. How do we relate them? Work energy theorem again. Okay, so we start with W equals delta K, okay, initial to final. Now, the work done, there are two forces involved. One is mg, the other is n, right? What is the work done by gravity? Well, this is work done by gravity, Wg, plus the work done by the normal force n. You have to consider both of them, right? The work done by gravity, we know what that is. That's mgh. It has nothing to do with the shape of the track. It's just how far it went down. Okay, question is, what is the work done by the normal force? Okay, well, let me work out this integral now. Express the integral n dot dr, right? That is the work done by the normal force, right? Again, we do not know what n is. It can change magnitude, it can change direction. The only thing we know for sure about n is this. And that is n is perpendicular to v, okay? But is that all we need to know to find the value of this integral? Yes, because you're moving in a direction that's perpendicular to the force n. How much work is done by the force? 0, okay? Because n is perpendicular to v. V is dr over dt, so n is also perpendicular to dr, not just to v. So this integral is 0, folks. Okay, that is really nifty, because we only know one thing about this force n for sure, that is it is perpendicular to direction of motion. Turns out that is all we need to know, because that renders the work done by this force 0. Okay, so let me make sure I highlight this. This is 0 since n is perpendicular to dr. Okay, so there's no work done by the normal force. And then the only work done is by gravity. And how much is that equal to? How much is the work equal to? The work equals to delta K, which is 1/2 m v final squared minus 1/2 m v initial squared. And immediately we can solve for v final. Again, cross out all the masses and you get v final equals to the square root of V initial squared plus 2GH. Wow, look at how simple it is. Indeed, the detailed shape of the track makes no difference. Okay, and this expression, in fact, looks very similar to the one you see here, except this is going downwards, so the increase is in speed, not decrease, and it's actually identical to the answer we got in the first problem, this problem. Okay, so whether you're looking at a free fall, projectile motion, or sliding down a smooth track of whatever shape, the final speed is the same if you have the same initial speed and it goes through the same vertical drop h, because regardless of the situation, the only force that did work was gravity. And how much work is done by gravity? mgh. It only has to do with the vertical descent, which is h, which is the same for all three cases. So therefore, the final speed is the same for all three cases. Now, this is quite interesting because it means that if you look at a particle starting from initial state, okay, initial position here, initial position, and ends up at the final position f, you can start from I and ending at f, but following different tracks. Okay, you can follow totally different tracks. You can follow a track like, let me draw it. So you can follow a track like this. You can follow a track like that. You can follow a track like that. It doesn't matter, as long as you go from initial to final, as long as there's no friction in any of these tracks, by the time we get to the final position, your speed is always the same. It is always the square root of V initial squared plus 2GH. Okay? It has nothing to do with how you get there, as long as there's no friction doing work. Now, does that mean it takes the same amount of time to go from V initial to final position? No, it only means the final speed is the same. Okay? And clearly, if you take a big detour, you're going to get there, after greater amount of time, because it doesn't make you go any faster by the time you reach the end, but you have to cover greater distance. Now, so there is an extended question after this. It's not entirely based on the work energy theorem, but I want to pose this question to you first, and that is, suppose you have to go from this initial point to the final point. You have a choice as to what kind of smooth track you should follow. You're going to end up with the same final speed, regardless of the track. But can you find a particular track which will take you the shortest amount of time to go from initial to final? Okay, we're looking to minimize the time. Do you think the answer should be just a straight line connecting initial with final, like this? Is this the path which gives the shortest time? Shortest time. It is the shortest path. That's for sure, connecting the two. But is this the shortest time? Shortest time? That's a question mark. You might think it's the shortest distance leading to the shortest time, but no. Because look, if you have an arbitrary path, not a straight line, okay, like this one. If you have an arbitrary path, then clearly it's not uniformly accelerated motion anymore, because you have a variable normal force, as long as it's not a straight line connecting initial to final. When you have a variable normal force, that will give you the variable acceleration. Therefore, you're not looking for the uniformly accelerated motion. Therefore, you cannot calculate the average speed as initial plus final over 2. Even though initial speed and final speed are always the same, regardless of the path, the actual average speed can vary depending on the shape of the track, because it's a non-uniformly accelerated motion, except for the straight line. Okay, so even though a certain path is a little bit longer, maybe, just maybe, it could have a greater average speed than V initial plus V final over 2, which is given by that straight line. So you never know. Okay, shortest path does not automatically lead to the shortest time in this case. What shape of the track does give you the shortest time? That is a problem you can think about. It's a classic problem, and that is it's called the curve of the steepest descent, or the curve of the fastest descent. You go from initial point to a final point somewhat lower than when you started. How do you get there in the shortest time possible? Okay, ignoring friction, of course. That is a classic problem, and there is a classic solution, but I can tell you the answer is not a straight line. You can think about that later. It's not something as easy as applying the work energy theorem. Okay, so these are some examples of application of work energy theorem, but there's all these problems from simple to harder have something in common, and that is our solution relies only on the work energy theorem. We didn't have to do anything else. If you know the work energy theorem, you can solve any of these problems. Okay, is that always the case? Well, turns out, no, it's not always the case. There are situations where the work energy theorem itself, just by itself, does not provide the solution. Because the work energy theorem only relates two states. You have to relate initial final state. If you only have one state, a single state, to analyze what happens at that moment, the work energy theorem alone doesn't do the job because it relates two states. Okay, so if you only have one state, you cannot use the work energy theorem by itself. What can you use though? Newton's second law, of course. Newton's second law is about one state. Okay, if you have two states, Newton's second law doesn't provide you the answer directly because it doesn't link two states just by itself. You know, it only tells you what happens if you give me the F at this moment, I tell you the acceleration at the same moment. So what if I have a situation with initial and final state, but in the sequence from initial to final, there is one particular spot or one particular moment or one particular state that you're more interested. Now, you want to analyze what happens at that moment. Now, to do so, you have to use Newton's second law, apply to that moment. But there are also two states leading, say, for example, from initial to final state, even though you're more interested in what happens at the final state. Then you have to apply both the work energy theorem along with Newton's second law. Okay, the work energy theorem takes it from initial to final state, and then Newton's second law can be used to analyze specifically what happens at the final state, for example. So in the next lecture, we're going to look at examples where you must apply both Newton's second law and the work energy theorem to analyze the situation. So that is in our next lecture.